All right, for those of you who I did not thoroughly discourage with that last lecture, this is chapter 2, part 2. We talked about the seasons and the sun, and now let's talk about what that creates, which is temperature and heat. So you got to think to yourself, what is temperature, right? I know it, but I can't describe it. In our case, we're going to measure this scientifically. Temperature is a measurement of energy. The kinetic movement, molecules, atoms are always moving. They're moving. The faster they move, the more kinetic energy movement they have, the more temperature they have. Conversely, if something has slower speed, we say that it has lower temperature. Now, we perceive temperature as heat because things that have a higher temperature tend to be hotter. So when we talk about the temperature outside, we're actually perceiving this energy with um, we'll talk about this later with moisture in the atmosphere. But when we talk about the temperature of some type of material, we're talking about the average movement of the energy within it. So molecules move quickly. They bounce faster in things with high temperatures, slower in low temperatures. So you can actually slow all molecular movement to a certain level. That is the coldest you can get because if there's no movement, there is no temperature. And that's called absolute zero. It's about 700 degrees Fahrenheit negative, but we use a special scale called the Kelvin scale, which makes it zero. So let's talk about scales real quick. Right? We talked about time scales and physical scales, but temperature scales. Most of us know the Fahrenheit system, right? Water freezes at 32, it boils at 212. Today it's about 85 degrees out. A lot of countries around the world use the Celsius or the metric system, where water freezes at 0 and boils at 100. There is a way to convert it. I'm not going to worry about it. Most of the measurements we give in this class are, we use both systems, so don't worry about that. But here's an example. This is Fahrenheit, and this is Celsius. So right here, at 0 degrees Celsius, that's 32 degrees Fahrenheit. So if it's 85 degrees out, your friend from Canada or Spain is going to say it's 30 degrees out, right? But the Kelvin scale, now the Kelvin scale is different. 0 degrees Celsius, 32 degrees Fahrenheit is 273 degrees Kelvin. And what do you notice right here? That as you get colder with Kelvin, there are no negatives. And that's why the scale was developed. When scientists do measurements, they often deal with negative temperatures. If you've ever had to do math with negatives and positives, you know that it can be very difficult. So on a Kelvin scale, there is no negative number. 0 is absolute 0, right? We talked about that. The temperature at which all molecular movement stops cannot be any colder. That is 0. And so everything in a Kelvin scale is positive. So next time you want to be all kind of, mess with your friends, they can say, oh, man, how hot's it going to be tomorrow? You say, well, it's going to be 303 degrees Kelvin or 86 degrees. So the next part is heat. So heat is what happens when we move the energy of two different temperatures. We have something of this material which has a temperature and something of this material it has a different temperature. And temperature wants to even out. And that movement of energy between those two is called heat. We experience heat. That's how you feel it, right? If you touch something with high molecular movement, like hot coffee, we feel hot. If you touch something like ice, we feel cold. But generally speaking, materials want to even out. The things that are moving faster want to slow down to the ones that want to speed up. They want to even out. And so we usually see this transfer from this coffee in the cup, which heats this coffee cup up a little bit. So some of that energy is transferred into the porcelain coffee cup, which is then transferred into the ice, which melts the water. Eventually, over time, this will all be the same. It's like if you have a glass of ice water. Eventually, the ice will melt and the water will all be one temperature. So heat moves between items, different materials, in three ways. So conduction is when two things come into contact. You put a metal spoon in hot coffee and the spoon turns hot. Direct contact. You touch a burning stove. Hot contact. When you have conduction, heat always flows from the high temperature object to the low temperature object. So in this case, a cup of coffee, the heat, the temperature energy in the coffee is going to flow to the spoon and warm it up. The spoon will not cool the coffee. So ironically, if you have a glass of ice water, the ice doesn't cool the water. The water takes the energy from the ice. Different materials conduct heat at different levels of efficiency. The higher this number is, the better the conductivity. Copper is a much better conductor of heat than sand, which is why we use metal for pots. Sand does not conduct heat very well. Now you're saying to yourself, well, how does that explain if I go to the beach and the sand is hot? That's because the very top level of sand is very warm, but it doesn't move that heat. It just keeps it. If you brush away the first inch of sand, usually underneath is ice cold, isn't it? The second way temperatures are transferred is convection, and this is the movement of mass within a mass. So you can have a mass of warm air in relatively cooler air, and it might rise, might flow. So convection is usually, it needs a fluid. There is no direct contact, but it needs a fluid like water or gas. A good example would be a lava lamp. Have you ever seen a lava lamp? You have oil that's colored, it's hotter than the water, and the oil bubbles rise. So if heat needs a medium, like either being touched or air, then how do we get heat from the sun? And the last one, radiation. And so this is where the energy, the temperature energy, is transferred by wave action. And so it can travel through space. It can travel through a vacuum. And this is how we get sunlight. We're going to talk more about that later on in a couple more chapters. So that being said, we can now look at the patterns of temperatures on the surface of the Earth. And the first thing is, how do we measure that? Weather stations, thermometers, rain gauges. This map shows all the known weather stations in the world. What I find interesting, and I think there's a point about this, if you notice, we don't have hardly any weather stations in the Sahara Desert. How do we know what the temperature is in the middle of the desert? First of all, why don't we have any temperature stations there? Because there's no people living there, right? So we can use mathematical modeling and say, well, we know the temperature here, 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 and here, and do our best guess. But look at other countries. There's more weather stations in the United States than Mexico. That also goes with funding. Some countries have more money, or it's a higher priority. Look at the number of weather stations in Poland versus the Ukraine. So what this just shows you is there's oftentimes it's called a bias in the data. You have to be aware of that. So, surface temperature patterns. Every place on Earth has a seasonality. There is a hottest day of the year and a coldest day of the year. And the difference between those temperatures, that range, is seasonality. So normally what we do is we look at, say, Chicago, and what is the average maximum temperature, say, in the last 50 years. So the hottest average day in the last 50 years, let's just say was 95 degrees. That's the average hottest day of the year. What is the average coldest day of the year over the last 100 years? And let's just say that it's 20. That means that the seasonality is the range between 80 and 20. Okay? Now, not every area has the same range. Okay? Some areas have almost no variation. In Singapore, near the equator, it stays basically 80 degrees years round. Some parts of Russia, it goes from 100 degrees in summer to a negative 100 in winter. What affects this? The biggest difference is elevation and latitude. Generally speaking, the further north or south you go, the greater the range or seasonality. Generally speaking, the higher altitude you go up into the mountains, the greater the range. Here's an example. Here's India, right? Right here, You can see it's very warm. But here you have the Himalayan mountains, the tallest mountains on Earth, Mount Everest, very cold. And here, the Tibetan Plateau. This land is very flat, close to sea level. Then you have the Himalayan mountains. And the Himalayan mountains behind it, the Tibetan Plateau, the land here is on average 4 to 5 miles above sea level, where it's only less than 1 mile above sea level here. So, high, low, and you can see the definite temperature difference. You also see that as you go south, it does get warmer, but you can see that it's actually warmer here than even though it is further south here. Mountains, areas of high elevation are always colder. So, just an easy rule of thumb, the further from the equator, the less sunlight, the less direct sunlight, the greater variation. Lower surface temperatures at higher latitudes. And this graph just shows you right here. If you start at the equator and head towards the latitudes of the poles, that the observed temperatures, for the most part, pretty much follow this pattern. This is the average of ranges of temperatures. The black line is the median, and this red dotted line is the mathematical model that predicts it. So you can see there's this general pattern. And if we look at a map, this is a map of average surface temperatures over the last, I say, 15 years. You can see that the hottest temperatures tend to be at the equator, the coldest ones near the poles. There are some exceptions. Here's the Tibetan Plateau, this kind of island of cold right here. Right here in South America, this very cold strip, that's the Andes Mountains, some of the tallest mountains in the world. Elevation. All right, we're going to pause right here. Chance for everyone to get up and stretch and shake out the sillies, and we'll come back in just a moment.